Welcome back to the deep dive. We often talk about the almost superhuman things modern AI can do. I
hmm
mean, you have algorithms that can master incredibly complex games like Go or classify data with just, uncanny accuracy.
Right.
But for years, there was this one glaring weakness, almost a pathetic one, the machine's ability to, well, create something new.
Precisely. Traditional machine learning, what we call discriminative models, they're masters of pattern recognition.
Okay.
They're phenomenal at telling you what something is, a dog, a cat, a fraudulent transaction. But if you've ever tried to have a genuine, flowing, or frankly, convivial conversation with something like Siri or Alexa, you hit a wall pretty fast.
Yeah, that digital shrug.
Exactly. They were great mimics, sure, but terrible creators. Original synthesis, that creative spark just wasn't there.
So let's unpack that. You can train an AI to beat a grandmaster, but you can't get it to write a truly original sonnet or, say, generate a photorealistic face of a person who's never existed. That fundamental limit just, well, it shattered in 2014.
That's the year. That's when generative adversarial networks, or GANs, were introduced. And this deep learning technique completely changed the generative landscape
How so?
because it uses not one, but two separate neural networks. And they're trained against each other in this fierce competitive dynamic.
And that architectural arms race is our mission today. We are diving deep into the competitive dynamics of GANs, tracing their history from, these simple generative precursors all the way to the photorealistic capabilities of today's cutting-edge models.
And we'll get into their applications, some revolutionary, some a little worrying across medicine, fashion, and security.
Okay, so let's start with the architecture itself, this idea of two networks competing. The classic analogy seems like the perfect entry point. A relentless art forger trying to fool an expert art critic.
It's definitely the most intuitive way to grasp the mechanics. So you have two key players. The first is the generator network. That's our art forger.
Right.
Its input is basically just random noise. You can think of it as a raw random blueprint, a seed for its creation. And its only job is to output a fake example, a synthetic piece of data that it hopes is completely indistinguishable.
From the real thing.
Exactly. And then the second player is the discriminator network, our expert critic.
Okay, and it's looking at both the real stuff and the forgeries.
Yep. It gets input from two sources, either a real example from the training data or the fake one from the generator. And its job is simple. Spit out a probability score. How likely is it that this image is authentic?
And then the training game begins.
They're trained simultaneously, and they're constantly improving against each other. The critic network, the discriminator, is trained to minimize its classification errors. It wants to correctly identify every real piece and successfully flag every forgery.
Meanwhile, the forger network has this opposite, beautifully malicious goal. It wants to maximize the critic's false positives.
It wins if it successfully tricks the critic into believing its forgery is authentic. It's this escalating arms race where every success for the forger improves its forging technique, and every successful detection by the critic sharpens its critical eye.
What's fascinating here is that this whole competitive dynamic is, mathematically, trying to find what's called a Nash equilibrium.
Right, that's a state of perfect balance where neither the forger nor the critic can improve its strategy any further because they've perfectly matched each other.
And here's the kicker, right? Finding that perfect, stable state is incredibly difficult. That's why early GANs were so notoriously unstable.
It wasn't just a tough math problem. Achieving convergence, that peaceful, balanced equilibrium, was a huge practical roadblock. The networks would often just spiral out of control.
Or even worse, they lead to what's called mode collapse.
Which is when the forger gets lazy. It finds one really good trick that fools the critic, and then it just stops inventing new things. It just repeats that one great forgery over and over again.
Before we jump into how we fix those problems, we really need to understand the world before GANs. We have to talk about autoencoders. They're often seen as the foundational models that came before.
Autoencoders are really elegant in their simplicity. They have two parts, an encoder and a decoder. The encoder takes your data, let's say a huge high-resolution image, and it compresses it. It squishes it down into a simplified, lower-dimensional representation.
And that compressed version is the famous latent space. So it's like a hidden, simpler map of the data's most important features.
Exactly. And the decoder then uses that compressed latent space to try and reconstruct the original image.
The genius here is that this enables unsupervised learning. You don't need labeled data, right?
Not at all. You just feed it the image, and the model learns by comparing the input to its own reconstructed output. And this is great for simple things like compression or, removing noise from old photos.
So if we had these models and they were pretty effective, why did we need the complex, unstable GANs?
The blurry problem. Autoencoders, especially the more sophisticated ones called variational autoencoders or VAEs, they just failed when you tried to push them to high resolution or complex data.
How so?
Well, they model that latent space by assuming it follows a simple, kind of well-behaved distribution. So when they're faced with really complex data, like the celeb data set of celebrity faces with all these diverse backgrounds, the VAE would always opt for the safe middle.
The safe middle, what do you mean by that?
It means the VAE knows what a good eye or a mouth looks like, but the backgrounds are just too varied. So to minimize its reconstruction error, the model just picks a compromise, an average pixel value of all possible backgrounds.
And the result is what? A blurry mess.
You get blurry textures, fuzzy backgrounds, no crisp detail. It's a safe bet for the model, but it's not photorealistic. That inability to generate sharp, truly realistic samples was the critical limitation that really spurred the need for the adversarial framework.
So the blurry problem created the need for better quality. And the first huge breakthrough in GAN stability and quality came in 2016 with the Deep Convolutional GAN, or DC-GAN.
DC-GAN was absolutely essential. It was the first to successfully figure out how to integrate convolutional neural networks, the backbone of all modern image processing, into both the forger and the critic.
But wait, wouldn't tying those really complex contents together make the system even harder to train? More unstable?
Oh, it created chaos.
Yeah.
DC-GAN's viability really hinged on one major stabilization technique called batch normalization.
Okay, what is that?
Think of batch normalization like the quality control department for the data stream inside the network. As data moves through layer after layer, it can change wildly. It might get really big in one layer or really small in the next.
So the input to one layer could be completely different from the input to the layer before it, which would just throw off all the learning?
Exactly. BN solves this by making sure the inputs to every single layer are standardized and consistent throughout the entire training process. It keeps the data flowing smoothly and predictably, which is really the only way these huge, deep, complex architectures can actually train without the system just spiraling into useless noise.
Stability achieved. But the next leap was all about scale. And that brings us to the progressive GAN, or PGGAN. This is the moment photorealism became a scalable reality, letting machines produce full HD, 1024 by 1,024 faces.
PGGAN uses this brilliant, almost gentle approach. Think of the problem like trying to climb a massive, jagged mountain in a single jump.
But you'll fail.
You'll fail. Instead, PGGAN uses a mountaineering strategy. It starts training at the base, a super low resolution, like 4 by 4 pixels. Once that tiny model is stable, it progressively adds new, higher resolution layers to both the forger and the critic.
So you're simplifying the problem first. You learn the big features like this is a face shape before you even try to learn the fine details like skin texture or individual strands of hair.
Precisely. And they made the transition incredibly smooth. They use a special parameter to gradually fade in the new high-resolution layers. It prevents a shock to the system. This bootstrapping method makes the whole training process dramatically more stable and allowed them to tackle resolutions that were, before this, just impossible.
PGGAN also introduced some really clever architectural tricks to fight that problem we mentioned earlier. Mode collapse, where the forger gets stuck in a rut.
Right. That was the mini-batch standard deviation trick. The big problem with mode collapse is that the forger isn't generating variety.
So it's not diverse enough.
Exactly. So PGGAN added a small statistical block to the critic that measures the variance within a batch of generated images. It checks if all the fakes look a little too similar to each other.
Hold on, mini-batch standard deviation, that sounds like a computational nightmare. Is the performance hit worth the stability gain?
Absolutely. The stability gains are critical. It acts as this explicit signal to the forger, basically telling it, hey, you are not being varied enough. It forces the forger to increase the diversity of its output, directly fighting that risk of falling into a single repetitive pattern.
That's a brilliant little trick. What about the second hack?
Pixel-wise feature normalization. This was in the forger, and it's another stability measure. As these networks get deeper and deeper, the internal signals, the feature activations, can just explode in magnitude.
Destabilizing the whole game.
Right. Normalizing these feature magnitudes for each pixel keeps everything in check. It ensures the arms race proceeds in a nice, orderly control fashion.
So PGGAN proved machines could be photorealistically creative, but standard GAN still lacked control. They just spit out an image based on the data. What if I want a specific output? This brings us to targeted generation and image translation.
This is where we introduce the idea of conditioning the network, basically giving it specific instructions. Let's look at the semi-supervised GAN, SGN first, which tackles the huge practical bottleneck of data labeling.
Right. I mean, labeling a massive data set like ImageNet took, what, 2.5 years of human effort?
SGN gets around this by giving the critic network two jobs. It still has to distinguish real data from fake data, but it also has to act as a standard multi-class classifier for the real examples that do have labels.
And the results are just stunning because that adversarial process acts like a massive turbo booster for generalization.
They are. In one experiment using a small piece of the MNAS dataset, a standard supervised classifier trained on only 100 labeled examples hit about 70% accuracy. The SGN, though, leveraging all that unlabeled data through its adversarial structure, boosted that accuracy by nearly 20 percentage points.
Wow.
It got well over 85%. It proves you don't need a million labels if you have a powerful generator to understand the underlying data distribution.
But for true item-specific control, we turn to the conditional GAN, or CGAN.
CGN lets us explicitly tell the forger what to synthesize. We feed a label, or some other conditioning info like the word shirt or the number 7, into both the forger and the critic. The forger learns to produce only images that match that condition.
And the critic learns to only accept real examples that are paired with the correct label.
Exactly. So you're not just generating a random digit. You're generating a 7 only because you asked for a 7.
Okay, and then moving beyond labels to full-on image translation, we have the brilliant CycleGAN.
CycleGAN is this general-purpose technique for translating an image from one domain to another. Think turning a summer photo into a winter photo, or famously, a photo of a horse into a zebra.
But without needing perfectly paired training examples, that's the key, right?
That's the key. Usually you'd need the exact same picture taken in summer and winter. CycleGAN just needs a big, unpaired collection of summer photos and another big collection of winter photos.
That sounds genuinely counterintuitive. How does it know that the generated winter tree belongs in the same spot as the original summer tree?
That's the core innovation, the cycle consistency loss. It enforces the simple rule. If you translate an image from A to B and then translate it back from B to A, you have to end up with the original image.
Ah, like a visual proofreader. It ensures the integrity of the translation.
It's just like back translation in language. If you convert the horse to a zebra, you must be able to convert that same zebra back to the exact same original horse.
That A to B to A requirement acts as this powerful constraint. It makes sure the networks are actually learning the meaningful differences between the two domains, not just, rearranging pixels.
And it has transformative applications, generating satellite maps from street views, changing artistic styles, and yes, turning apples into oranges.
We've seen the versatility, but now we have to talk about the real-world implications, especially in defense and commerce. The competitive dynamic of GANs is actually very closely related to the idea of adversarial examples.
They're conceptually identical. Adversarial examples are those tiny, intentional tweaks to an image that are invisible to a human eye, but cause an ML model to completely misclassify it.
Like classifying a stop sign as a speed limit sign.
Exactly. And the way you create those is just like the forger network trying to fool a fixed critic network.
But what's encouraging is that this realization has also led to GANs being used as a defense.
It has. If the adversarial attack tries to push an image off the learned distribution of real images, some defenses actually use a generator to pull that compromised image back onto what the system knows as the real data manifold before classification.
It's like cleaning up the image before the computer even looks at it.
Exactly. And outside of security, the practical applications are moving fast. In medicine, for example, DCGAN has been used to augment data sets, which are notoriously small because patients' conditions are often rare.
Medical imagery is the perfect example of a data-constrained field.
Absolutely. One study on liver lesions showed that when they used classical data augmentation, just rotating or flipping images, their accuracy plateaued at about 80%. But when they added GAN-generated synthetic examples that were truly novel, they boosted classification accuracy to over 85%. That 5-point jump is massive in a medical setting.
And in commercial world, conditional GANs are driving hyper-personalization. We're seeing major retailers like Amazon experimenting with CGANs as a kind of digital tailor.
That's a good way to put it. They find the underlying feature vector that corresponds to a specific garment, and then they can iteratively adjust that vector in the GANs latent space to optimize the generated item for an individual shopper.
So they can optimize for fit, color preference, style score, creating a product that is literally unique to you.
Hmm?
But the most potent, and I think maybe the most troubling application comes from the sheer photographic realism that PGGAN enabled. We are talking about the ability to generate hyper-realistic synthetic data, especially video footage deepfakes.
This capacity for deception is really unprecedented. The systems are so sophisticated now that they can swap faces or generate dialogue seamlessly.
Yeah.
The ethical concern isn't just that these videos exist, it's the enormous scale at which credible fake news and misinformation can now be generated and spread.
Fundamentally challenging our trust in digital media.
It really is.
So where does this all leave us? We have journeyed from this conceptual competitive game of the forger versus the critic. We've traced the breakthroughs that stabilize these architectures, from batch normalization's quality control to PGGAN's progressive gentle scaling.
And we've seen the sheer versatility of conditional models like CycleGAN across applications from medical diagnostics to personalized shopping.
And if we connect this all to the bigger picture, GANs have undeniably achieved remarkable results. They've earned this reputation for giving machines the gift of creativity. But let's go back to the core function. The forger network's training requires it to mimic the patterns of the data it sees.
Right. And since GANs, by their very nature, cannot stray far from the distribution of data they were trained on, are they truly creative entities? Or are they simply the most sophisticated and powerful mimics we have ever built?
A compelling thought to end on. If the system is just getting better at repeating what's already seen, where does human creativity stand? Thank you for joining us for the deep dive.